My name again is Geoff Burr from IBM Research, and it's a great honor to be here today representing my many colleagues who work at the AI Hardware Center. And the title of my talk is Advancing Broad AI with Algorithms and Architectures for Digital and Analog AI Acceleration. So to segue into my first slide, I thought it was a good point to point out that many of us accessing from home, we're learning a lot more about virology and epidemiology and all sorts of things in biology that we knew before. But it's also important to remind you that this AI area also advanced from biology. And this is one particular person who made that possible, Santiago Ramon y Cajal, who won the Nobel Prize, I believe, in 1906 or 1908, around there, for really understanding how the central nervous system works breaking out sort of the concepts of neurons and synapses, making these nice drawings, things that eventually, 50 years later, led to the mathematicians putting together what became the first artificial neural networks, the perceptrons. This particular manifestation here is a convolutional net that was invented in 1999. The interesting thing about this deep learning AI that we are doing today is the algorithm that we are using to train these algorithms is exactly the same algorithm that was invented in the mid-80s. I learned in grad school in roughly 1991. It's called backpropagation. And so the way it works, you like to use these convolution filters because they have shift invariance. So as you move the filter across the apple, it will learn where the stem is on an apple or what the stem looks like, no matter where the apple is shifted in the image. So that makes convolution networks great for image processing. The way the backpropagation works is you show it examples of what you want. You have a label. You propagate through the system. Originally, the weights are all random. It makes a total guess. You tell it no apple is to the one it's supposed to be. It backpropagates. It makes a small change to the weights in such a way that it will do a better job of recognizing this apple, classifying it as an apple the next time that it sees it. There is absolutely no promise that the weight changes that you make here and here independently will work together. It just turns out that happens to work. There's no promise that the weight changes you will make for a banana you look at right afterwards will not undo this problem of apple. None of that is mathematically promised. The only thing that's mathematically promised is those weight changes will essentially move towards a gradient descent that do better at classifying the apple. But somehow the whole thing works. Again, in the late 80s, early 90s, the people who were propagating this algorithm or promoting this algorithm did not have any proof that it was truly scalable. That proof did not come until probably 2010, 2012 timeframe, where we took, first of all, the ability of the internet to disseminate large data sets. So rather than people going to conferences and complaining that my apples are easier to classify than your apples, instead we had things like ImageNet that could be shared over the internet. So that was the second leg of the triad. And then the third leg of the triad were all those GPUs that the teenagers were using to play video games. They turned out to be really, really good for the matrix manipulations that are here. So those are the three legs of the triangle. And then we could empirically prove that this backpropagation algorithm was really scalable. So that has put us into and through the era of narrow AI. It's probably past emerging. We need to change this label. It's focused on this deep learning that I just talked about on the previous slide. It's really good at a single task in a single domain, and it can get to superhuman accuracy. We've seen that in a number of different fields. It has a slight weakness that it requires large amounts of labeled data. This then also leads to the problem that data becomes really important, and large companies that can suck in large amounts of our data are going to do better at this, which leads to all sorts of privacy concerns and so on. So it'd be better to have systems that could, like humans, learn from a small amount of data. And then, of course, they're focused on CPU and GPU. So we're now at this regime where we want to essentially make custom hardware. And most of my talk will be about reduced precision, and in the second half I'll talk about analog hardware to essentially go beyond CPU and GPU to move from narrow AI into this broad AI. We want to make this, both IBM and many players in the industry want to make this disruptive and pervasive. We're working on things called neurosymbolic AI, combining the deep learning with some of the other benefits, or other AI phrases, and I will have a slide to make it more clear what I mean by this phrase. Instead of just being in a single task and single domain, we want to move to multitask, multi-domain, and multimodal. I'll have a couple of examples of that. And then we also want to be able to learn with less data so we can use it in more areas where we don't have as much data. And then we can also start to trust the thing and also not have the importance of all the data. Or I'll give you an example of where we can have something that harnesses large amounts of data, but actually does not need to move it, so it stays private and protected, and yet we harness the benefits of learning from large amounts of data. And now, of course, this slide also includes this area of general AI to the right here, which is truly revolutionary. We have no idea how long it will take to get to this point, so it's really not too much I'm not going to have any discussion on that in the slide deck. So we put together an example of the kind of things that IBM clients care about. All of these are based on vision. We could have easily made a slide based on also natural language processing, processing documents, processing speech, and things like that. But in areas ranging from construction to insurance, there were lots of talks earlier today on automotive, earlier this week on automotive. And I will, in a couple slides, have a specific example on sports video action. But you can see how even for a company like IBM that is not consumer focused, but focused on enterprise clients, there's still lots of reasons why you want to build systems that go from narrow AI to broad AI and focus on images. So here's some examples where we talk about multi-modal models, being able to deal with different modalities coming from different sensors. In this context, it was in the context of autonomous driving. This is not just multimodal in terms of having an image and then being able to answer a question in text, but also gives us an example, to describe what I understand is neurosymbolic reasoning, which is rather than using backpropagation and deep learning to build something that automatically recognizes this image, instead you build something that trains to essentially build a program, and that program allows you to answer the question. So the AI, it works with these symbols and essentially writes programs which then can interrogate the scene and answer a question posed in text. And then on the right, we have the security and privacy, the idea that we might have a customer that has a bank, and he works with a consortium. You have requirements on the data that they, for instance, maybe they cannot leave the US or they cannot leave Europe. And yet you want to build a system that can learn from all these pieces of data without violating those requirements for compliance or requirements for security, privacy of the data. So you have ways to do federated learning where you can extract the knowledge from those without actually moving the data or violating any privacy constraints on them. So as I promised, let me see if I need to turn up the volume here. Hopefully you'll be able to hear.
Kaki sent the ball to McGeady. McGeady sent a cross, and it's stopped by the goalkeeper. Randall sent the ball to Hernandez. And here comes the cross. Hernandez is making an attempt. This ball is going nowhere.
So I hope that came through. So all of that was automated. It's basically an automated play-by-play call, a system that does end-to-end learning, feeding in the video, the data feed and stats, external knowledge about the game, and essentially doing end-to-end training to be able to recognize the action, understand the context in which actions are taking place, and actually churn out, in this case, what you heard was a play-by-play game call. But the idea would be to expand even further on that, be able to do color commentary, like, for instance, compare that goal versus when was the last time that player scored a goal, or so on and so forth. So to be able to do things where people have personalized narration. So this is an interesting kind of cool example from my colleagues in IBM research that we wanted to show to you. So after that introduction, let me drive into the main topic, which is to essentially try to build more energy efficient hardware. So even this narrow AI, and not just the broad AI, requires a lot of computational horsepower. So this is a well-known network, ResNet 101, working on the large ImageNet database with many different layers. And if you want to train this, whether you own just a few GPUs or you go out and buy a lot of GPUs, you still are investing enormous amounts of power. And you, of course, have to spend more money to be able to do it faster, but the amount of energy that you spend is equivalent to 2 weeks of home energy consumption. And this trend is only going to get worse. So if this is a well-known plot from the OpenAI folks, it's a very cool plot The vertical axis is petaflops per second per day. So when you're at 1.0 here, you basically set up your rack that can do 1 petaflop per second, and you ran it all day. And that is that data point there. So you can imagine these ones to essentially do well at Go. You are basically doing a lot more than that, or you're doing a lot more days. And this trend is extremely steep. The amount of investment that we're doing in the total number of flops that you have to do the training is doubling every 3 to 3.5 months or so. And so this is an unsustainable curve unless we have significant hardware and software innovation. Not just sort of the next products, but really allowing ourselves another order of magnitude or several orders of magnitude in terms of energy efficiency. Because we're still going to need to do all these flops, but the idea is, can we do it in smaller volumes and with smaller amounts of total energy? So what we really need to do is to continue to improve this curve of gigaops per watt. So we'll still need to do those many teraflops. Teraflop is about right here between 10 to the 2 and 10 to the 3. So this is a teraop per watt, and that's right about where products are coming out. They're already exploiting reduced precision. We're already seeing most products for training talking about B-float, and most products for inference talking about 8 bits. What I'll show you in the next couple slides is the next trend beyond that, where we are trying to push in our digital stuff down even lower in bit precision, so that we can continue this trend and essentially implement this data point of energy efficiency. So that'll be my next part of my slides. So I'll get into the section from the digital AI core team, my colleagues who work on digital accelerators, and they have really been at the forefront of approximate computing. I'll show you one of their early papers from 2015 that has been widely referenced. I have many slides from them on their quantization techniques, so I won't try to talk about them over this picture. I will talk about compression in the context of training, when you have distributed training and multiple workers working together to train a very large model. The naive thing to do would be to send all the weight updates between each other, peer-to-peer, or to some sort of mothership. So it can correlate all the weight updates that have been suggested by the different workers, and then send out which ones should be used to all the workers. And as you can imagine, there's an enormous amount of network bandwidth that would be required to support that. So what my colleagues in this team have focused on is, well, what weight updates do I have to send over the network? Can I really reduce the network bandwidth needed by being very clever without really costing much in terms of convergence, and still having the benefits of the model that is trained over 32 workers is much, much better than could have ever been trained on any one worker by itself. I'll talk a little bit about the center column here, the programming model. This is, again, to reduce the communication load, but essentially to do the programming in a way where you parallelize as much as you can, but you avoid having essentially workers freeze because they're waiting for someone else to respond. So in the programming model, you have to be clever on how to do this. You also have to do this in a way that extends the programming back all the way back up to the high-level frameworks like TensorFlow or Caffe or PyTorch and so on, so that the people who buy this hardware and use it are essentially using it just the way they would use a CPU or GPU. They really cannot tell the difference, other than everything goes a lot faster. And the box that sits in my office or in the server room is now much smaller. And then my colleagues are working on architecture and turning that into hardware. And they have published a paper in VLSI 2018. So rather than talking about this small version of the picture, I'll go to the next slide where it's a larger version of the picture. So again, this is a couple years ago in VLSI 2018. I know that they have a talk that's accepted for VLSI circuits 2020. So when you attend VLSI in June, probably virtually, you'll be able to see what they have as the next turn of the crank after this idea. But in all cases, all their designs are designed from the ground up for reduced precision, deep learning acceleration. And when we say reduced precision, we mean all the way down to 2 bits, but also hardware that can flip back to 4 bits when you need it, or flip back to 8 bits when you need it, using the right bit precision in the right place. So again, it's a designed from the ground up as an accelerated plus memory architecture to orchestrate the computation and the data movement from the scratch pads through the PEs, through the special function units, back to the scratch pad, in a way that on a large number of workloads, not just these image processing ones that are shown here, but a large number of workloads for NLP or for speech, that you are getting utilizations that are regularly well above 90 to 100%. And this is without having to exploit sparsity. It turns out, my colleagues, the approach they have taken is by the point you get to 4-bit or 2-bit activations and weights, it actually is more costly to use sparsity unless you could guarantee you're going to be at 90%, 80% sparsity. At only 50% sparsity, it's actually better to just assume you need to operate every weight and every activation and not put in the extra circuitry to check that if there are zeros. So that's the approach that my colleagues have taken. Again, plot on sort of cartoon number of bits versus year. This is a paper that they wrote in 2015 where they did stochastic rounding for the first time. I believe I've seen many, many times people doing digital accelerators where they reference this paper. This is the one that suggested stochastic rounding. The issue before this paper was that when you reduce the bit precision, the smallest thing you have in the system are the weight updates. And when a weight update is well under 1 LSB, then it basically rounds down to 0 and the training stops. And this introduced the concept of stochastic rounding, which I believe everybody uses now. So over the next couple of slides, I will go through both of these curves. I'll show some results from this work on 8-bit training, where they've moved beyond just stochastic rounding, and now they're able to do full training on a wide variety of models using literally 8-bit floating points. And then I'll switch over to the inference. I probably don't have any slides from the 4-bit inference, but I will show slides from the 2-bit inference. So in both this case, the 8-bit training and the 4-bit inference, my colleagues are exact ISO accuracy, not just off by 1/10%, but exact ISO accuracy. So let me start that. I'll start with the training bit. So this is maintaining model accuracy with reduced precision computation, showing test error going down as you train. The black line is the baseline, what you would expect. For those of you who have not done a lot of deep learning before, this hitch here are where you drop the learning rate. So you've gone along with, say, 30 epochs for some learning rate, and you drop the learning rate, all of a sudden the accuracy goes way down. If you do this too early, then you will essentially not be able to converge. So one of the aspects here is picking when to do this learning rate scheduling. There's obviously lots of different options to do that, but if you choose the options for 32-bit and for 8-bit, you can see you get exactly the same error rate or accuracy by switching to a floating point 8 format. And you essentially do 2 different formats, one for accumulations and one for the weights. So it's 1 sign bit, 5 exponent bits, and then only 2 mantissa bits. You do the accumulations in 16-bit locally. You're not shipping weights or activations. But you accumulate in 16-bit, and then you get it back down to floating point 8 when you need to send it around. You include the stochastic rounding I mentioned, and you're very careful about the loss scaling. If the loss is too small to be delivered here, you might multiply it by, let's say, 47 to deliver it around an FP8, and then when the gradients are actually tweaked, you bring in that scaling coefficient of 47 back in, so that you can use the dynamic range of the floating point 8 wisely. This is results from 1 year later, 2019, where they did not just the base visual processing models, but visual processing models that are much harder to train, for instance, mobile nets, and then a wide variety of NLP and speech models. Here again, the trend is the same. You have 16-bit accumulations for errors and activations on forward and backward, but you're alternating between 2 different floating point 8 models. In the backward one, you want to accumulate the errors with 5 bits of exponent and only 2 bits of mantissa. And by doing this appropriately, what my colleagues show, this on the next slide here, is that you can go from the baseline performance in terms of whatever units that is, and you can get exactly the same performance, if not even better, by essentially doing the floating point 8 training in the right way. So it completely preserves model accuracy across a wide spectrum of deep learning models. I think on the next slide, I'm going to pick out 2 of them, which is this mobile net, and I'm going to pick out, I believe it's this transformer, and I'll show you the specific examples, because these are 2 very, very difficult ones to achieve this kind of performance on. So again, this is test error as you train in the epoch. I believe the dotted line is the baseline, and the solid line is their hybrid floating point 8. And so not only for the base model mobile net, but also for smaller versions of it, the official 0.35 version that is much harder to train, they're actually getting ISO accuracy across all those models, no matter how challenging they are. This shows a transformer in English to German translation, baseline in blue, the floating point 8 in orange, showing either the blue score, which is basically the raw translation performance, as well as the training loss. The orange and blue curves are right on top of each other. So they're getting ISO accuracy with this hybrid floating point 8, even with these most highly constrained models. So let me switch from training to inference. So in inference, my colleagues, these slides basically assume we've already succeeded at 4-bit. So when you have 16 levels to place, you're at ISO accuracy. So all these slides are from their most recent presentations where they're trying to achieve that also with 2-bit. And as you might expect, 2-bit is even harder. You only have these 4 slots that you can put on your distribution of weights. And you have to make a choice as to where you set your clipping level. And if you set it too low, you won't have much quantization error. The orange curve will be really low. But then you'll have a lot of clipping errors. Those large activations, they may be rare, but when you lose them, you lose the ability to converge your training. And vice versa, if you are very expansive with how you clip and you push this way out here, you're going to reduce that error from clipping, but you're going to have a lot of quantization error. And in their paper, they point out that, of course, if you don't have their particular algorithm, you can go and exhaustively try each one of these choices and pick the one that's best. They have an algorithm they call PACT, parameterized clipping activation, where it goes and tunes this clipping level, and I believe it does it at every layer, so it sort of automatically finds this nice notch as it's doing the training. They also have schemes they call statistics-aware weight binning, where they look at the statistical distribution and adjust their 4 bins to appropriately to represent that weight binning. And then a subtle point is the shortcuts in something like a ResNet. You do not want to do this quantization, the red box here, you do not want to do it before the shortcut. The forward pass will work okay, but when you do the back propagation and propagate the gradient backwards through this black line, you will lose a lot of performance there, and you will not be able to converge as low. So you really have to apply the quantization after the shortcut, save the fully quantized shortcut value and apply it here, and that will be the way to help you to get to better accuracy. So again, they pointed that out in the paper. So here are some results, again, with 2-bit weights and 32-bit activations, vice versa, 32-bit weights and 2-bit activations, and then with everything in 2-bit. And you see they're still losing about 0.7%, so they have not declared victory on ISO accuracy. On ResNet 50, for instance, they still have 2 to 3. For 4-bit inference, they have declared victory. They're at ISO accuracy, and they believe they probably need another 9 to 12 months to work on the algorithms to be able to get ISO accuracy with 2-bit inference. But when you look at all the other 2-bit modes, they have the lowest degradation, but not ready yet to declare victory. So that's why this dot occurs over 2021, is that it will take them a year or so to have this 2-bit inference ready to go. But as you can see from the published results, they're already pretty close. So with that, I'm going to switch gears. I've shown you this slide already in teraflops per watt, gigaops per watt as a function of year. And we think with those approaches, we'll be able to extend the next couple of years and push down to 8 bits in training and to 4 or even 2 bits in inference. But in order to continue this curve, we need something different. And we might need essentially a change in the compute paradigm. And the one that we're interested in and we're looking at is to go to analog, to essentially do the multiply accumulates in the analog domain all in parallel. And so I have a couple slides. This is actually the area that I work on. And so I'll have a couple slides to talk about that. And we work on this because it could potentially offer another 100x in energy efficiency. However, I will point out this is very much in the research domain. It is still entirely possible we will do the research and decide that, yes, it could deliver this, but it's not going to deliver the accuracy, or it's not going to be low enough area to be interesting in cost. So it's still very much in the research domain. But it is very, very exciting in terms of the potential that it could have. And by eliminating the von Neumann bottleneck using these, what we call resistive processing units. And so these are little analog resistors. If you broke open one of the 3D crosspoint devices from Intel and Micron, you would find something physically in there that acts as one of these resistors, a phase change memory device. In the context of memory, it's just used to store zeros and ones. But what you would do in this context is tune it to an analog conductance. And you would encode your weights of the neural network into these conductance that you physically have sitting on a crossbar array. So it literally is in-memory computing. You have an analog memory, and you query it in place. So when you encode the weights into the conductance, you encode the excitations either into the duration of voltage pulses or into their amplitude. There's 2 different choices you can make there. And essentially, when you apply this voltage to this conductance, and V equals IR, but I equals V times G, so you have V times G. So you just did the multiply in the current, the trickle current that's coming through this resistor, which is exactly the same thing that would happen in the memory. Now, unlike a memory, you're going to apply voltages to every single row simultaneously, which means there's trickle currents in each one of these resistors, and they will all sum up by Kirchhoff's current law. So you've done the multiply with Ohm's law, you've done the accumulate with Kirchhoff's current law, and you have the result down here on this capacitor that you can turn into ones and zeros and send to the next array, or there are other ways to do it. So it's really, really quite attractive in the sense that if I have 1,000 by 1,000 crossbar, I've just done 1,000,000 multiply accumulates in parallel at the location of the weight data. Not only did I, in my previous section, we talked about moving 2 bits for the weights or 4 bits for the weights. Here, this is completely weight stationary. The excitations come to the weights. And this is particularly useful for neural network layers with a small amount of weight reuse. So we've shown, we've built a full 90 nanometer design and looked at the energy assessment of it. And we get very, very impressive teraflops per second watt numbers with real phase change memory characteristics, especially if we decrease the conductance. So what this shows us is the analog AI can provide high performance in terms of high throughput and low latency, and at the same time high energy efficiency or lower energy and power. But it's especially true for DNN layers with low weight reuse. With things like convolutional networks where the weight reuse is extremely high, we're always highly energy efficient, but it's a little bit harder to get high performance in terms of teraflops per second per square millimeter. But these kind of layers are the kind of layers that are very hard to do on digital circuitry. So we really feel there's a very strong complement between analog and digital. I mentioned the ADCs. We have to be very careful and very efficient with those ADCs in terms of the area and power that they require, because if we're not, then that will depress this curve quite a bit. And then we need the analog memory devices, and I have a couple slides on those in the remaining of the talk. We need them to be robust and highly resistive. Right? As the resistance goes up, I will be able to move from left to right. And in that read process, where I'm reading not just one row, but I'm reading the entire array, that read process becomes more and more efficient, allows the energy to drop in the read process, and essentially the teraflops per second to get well over 100 or even closing in on 200 teraflops per second per watt, teraflops per joule. And of course, this works for both inference and training. Training is more complex, so it has more circuitry, so you're spending more square millimeters and getting less teraflops per second, but it is possible to do both. And you want different kinds of devices for both. So to encapsulate quickly the benefits for inference, you're doing the thousands of multiply accumulates and operations in parallel. For training, you get that, and you get the idea of doing parallel with in-place weight updates. That once you have the excitation vector that was used during the forward pass, you have the delta vector that was used during the backward pass, which you can do in place. You basically can operate on the transpose of the matrix in place, and then you can do the weight update in place entirely parallel across this whole array, provided that you have the right response in this crosspoint device. And I believe that's the next thing we're going to talk about. So the ideal response would look something like this. When I look at conductivity as a function of the pulses that I'm applying, no matter where I am in terms of the conductivity, whether I have a large weight or a small weight, when I ask, the neural network asks the weight to go up or it asks the weight to go down, that change in conductance is the same. Our most mature memory device that we're working with is called phase change memory. This is a sort of a stylized cross-through of how that device works. It has a top electrode, a bottom electrode. We've made the bottom electrode very small so you get heating. And when you can either make an amorphous plug by heating up to, say, 600 degrees, a very small region, and quenching, and you'll get a very, very high resistance, or you can apply pulse after pulse to crystallize it. That pulse after crystallizing it looks like this sort of slow, gradual update. It has a little bit of curvature to it, but it's not bad. But the amorphous plug causes a problem. When I want the conductance to go back down, I either make the entire amorphous plug or I don't. So this curve does not really resemble what we have over here. So that's an incentive to fix it. We'll also have an additional problem. You can still use this for inference, that is, use this curve to tune it to a conductance value that allows you to represent a pre-trained model and then do inference on it at very low power. The problem is once you make this amorphous plug, it continues to relax over time. So these conductances will actually slowly change over time. So we've been working on a number of things to address all these things in the context of minimum drift. When we make this amorphous plug between the top electrode and the bottom electrode for phase change memory, what we do is we have a huge contrast here. The contrast in resistivity between the red stuff and the yellow stuff is 5 orders of magnitude. So it's very easy to make a device with 2 orders of magnitude resistance contrast. So we can throw away a little bit of that, sacrifice a little bit of that resistance contrast by intentionally shunting the device with something that has exactly the right conductance. When we melt it, when we put a lot of current, we get melting in the center, we get this amorphous plug. But when it comes time to read, then the read current will sample the yellow stuff, and then it'll go into the shunt layer and then back into the yellow stuff. This throws away maybe, or gives away 5x to 8x, 10x of the resistance contrast. But what it does is that the read current is no longer sampling this red region that is relaxing, and it greatly reduces this the drift that's happening. So even though this part is changing in its state, the read current doesn't care because it doesn't go through it. So that's one approach we're taking. Another approach is to work to devices that are more symmetric. So this is RRAM, top electrode, bottom electrode, the same high K metal gate material, hafnium dioxide, or something like that. We move oxygen around with pulses. So pulse after pulse, the read current of the device can go up and down by changing the polarity of the device, shoving the oxygen ions up or shoving them back down. So we've shown some nice results here in working towards getting this to really look like a very, very uniform sawtooth curve. And then we've also been inspired by some friends at Sandia. We have a project now to do this 3-terminal device. This is like a little tiny battery. You have a material here that's going to store ions. It's going to change its conductance when you push in more ions or pull out more ions. And as you use pulses of different polarity, you can push the ions in, you can push the ions out, and you get a very, very nice curve here. The main problem, the reason we can't switch to this yet, is this 1 second is way too long. We need that probably 6, 7 orders of magnitude faster. But this is very, very, very promising in terms of this linearity and symmetry. So that's a material system we're working. In terms of training, in the same way that when you use a digital accelerator with reduced precision, you are going to train specifically for that bit precision. You can also do the same concept in analog. You can incorporate the analog deficiencies in a generic way into the forward training paths as you build the model in such a way that when it comes time to do the inference, and these curves are done with basically every error that we know of, essentially with the knob turned up to a very large degree, and showing that, in situations where the floating point essentially already has trouble, before we turn on this noise source, we already have many, many noise sources that are making the test error go high. By essentially just customizing the training for the analog hardware in the same way you would do quantized training for digital, you can get all the way back down to the nice low test errors on a wide variety of networks. So we really feel in the same way as quantized training, quantized neural networks for digital inference, you will want to do this kind of thing where you train carefully for the analog. And then in terms of an algorithmic approach, where even if we're not able to make these devices that are linear up and linear down, my colleague Typhoon Goffman has come up with a very neat idea he calls a tiki-taka algorithm. In contrast to the standard stochastic gradient descent algorithm, where the weights essentially take an input and produce an output. During training, the output becomes an error. The error goes through the transpose of the matrix and produces essentially more errors, and you use X and delta to update the weights. So in contrast, you do the same forward pass, you get the X and the delta, but you don't apply it directly to the weights, you apply it on this A matrix. The A matrix then manipulates into a vector, and that vector is used to update the C. So it's a sort of a tiki-taka. The soccer ball goes back and forth between the red part, which is the A matrix, and the green part, which is going to be the C matrix. And that allows you, what that allows you to do is do something that has a conductance response like this. So conductance as a function of the number of pulses. This is clearly not what we wanted. This is clearly nonlinear. And if you do the standard stochastic gradient descent, well, you'll notice that because you cannot converge this thing to a low enough test error. But with exactly that same sort of device put into this tiki-taka, exchanging back and forth between these matrices, you're able to match the same accuracy you would get with full digital precision training, of course, with all the energy benefits that are promised by analog AI. So I just have a few minutes left. I think I'm going to finish a little bit early. But I want to point out all this work is done as part of the IBM Research AI Hardware Center. We just celebrated our first birthday, first anniversary, just a month or two ago. So it's about running for 14 months now. we partner with partners with cross-industry ecosystem partners, so a lot of our IBM clients that are interested in working with us on this, and together with academia in New York State. The AI Hardware Center is located or centered in Albany, right next to the SUNY Albany campus, where we have a 300 millimeter sort of fab that we can work with in an exploratory way. We have a large investment from New York State to help us do that. We have our Watson Lab, a very large center of our research area center, just down the road from Albany. I myself work in the Albany Research Center, so I collaborate very, very closely with people here. And we're also, of course, collaborating with our team in Zurich, the Zurich Research Laboratory, and in Tokyo, and the Tokyo Research Laboratory. So all of us working together. Particularly the analog AI expertise is actually centered in Zurich and Albany and Tokyo. So there's one part where we really truly have a global team, and we enjoy very much working with our colleagues on the East Coast. So with that, I'll summarize my talk. So computational demand for AI models is growing extremely rapidly at a rate that may not be sustainable. Approximate computing techniques can successfully achieve ISO accuracy. No matter how complex and constrained the deep learning models are, we're able to show that this hybrid FP8 for training is exactly achieving ISO accuracy. Int4 for inference is exactly achieving ISO accuracy, and we have early results that Int2 looks like within a year or so we will also be at ISO accuracy for inference across a wide variety of extremely complex models with ability to support into the future as new models are extended from the building blocks that we're already using. And the whole point is not just to make these techniques, but to design and implement more efficient digital AI accelerators. I hinted at that a little bit. I'm not able to show you any specific results from either the digital or analog accelerators, but that is definitely the point. In the analog AI part, I showed that in-memory computing can provide both high performance and high energy efficiency. So we can go faster, we can deliver the results with lower latency, and we'll be able to reduce energy and power for both training and inference. Training is a little bit more difficult because we need the right kind of devices. With inference, we believe we already have the right kind of devices. And the point now is to show that this really will deliver this to the point where that it makes sense in doing the kind of work to make this possible. With this kind of work, you can go to a fab today and have this made. With this one, you're going to have to work with fabs to make new unit processes to support these phase change or RRM devices. That's going to be a significant investment, significant effort, and it only makes sense if this really, really pans out in terms of we're sure this is going to be so impressive that it makes sense to put in that energy and time into making those capabilities in fabs. So as throughout the talk, there's a lot of co-development, a lot of aspects where you have to know a little bit about hardware, a little bit about circuits, a little bit about algorithms, everything together. And so we feel that reduced precision digital and analog AI would definitely require co-development of algorithms, architectures, and even beyond that, circuits and devices. And all this is essential to achieve and maintain ISO accuracy. So with that, I think I would like to finish. I'd like to thank many colleagues who have helped me and taught me throughout IBM research. Particularly, I'd like to thank Dr. Kailash Gopalakrishnan, who leads our digital accelerator team, for giving me the slides in the first part of the talk and also explaining them enough so that I wouldn't embarrass myself when I presented them. And I'd also like to thank Dr. Cindy Goldberg, my colleague, who helped me put together this, and our colleague, Mike Houston, who is sort of our IBM contact who helped us interact with Linley. So I'd like to thank everyone for their time, and I'm happy to answer any questions.
Okay, thank you, Jeff, for that presentation. Very, very interesting material. So we will be taking questions from the audience. You can submit questions using the Q&A button. If I can just start, Jeff, with a couple of questions. So the data you presented using the hybrid floating point for training was very interesting and compelling, I think. But most of the training today in data centers still seems to be done in FP16, even though that paper was published a couple years ago. What are the barriers toward getting this actually adopted in the data centers?
Okay, so obviously the barrier is the hardware has to exist. The software stack has to be there that fully supports the same frameworks that everybody would use today is CPU and GPU or these new digital accelerators. support for Onyx, things like that. That is part and parcel. Any team that wants to deliver something like this has to be able to cover something all the way from the base hardware all the way up to just below the frameworks. Otherwise, or you have to be working with ecosystem partners who deliver that. And one of the benefits of IBM is we have all the expertise to do all those layers. Plus, we also have internal people who can basically help us work through all the workloads before we even start talking to other people. And so that is the approach that we're taking, is we want to design, not just design hardware, but supply the full software stack. And then, as long as we're talking about this down the road, the plan is for the analog accelerators. I do not believe there will ever be a hardware part that is a pure analog accelerator with no digital circuitry on it. I suspect it will always be hybrid. There'll be SoC that has a digital chip and analog, or one chip and one foundry that eventually that has everything in together, so that you don't have to go off chip to go from the digital to the analog part. And then, as with any part, even today's NVIDIA GPUs, you have some tensor cores and you have some 64-bit cores. You have to make a decision of how much you provision in each one. And then in runtime, the runtime code needs to help you decide, where do I provision this across the resources that are available on the part? And all that needs to be transparent to the deep learning customer running their models in a framework.
Great. And Jeff, on the analog side, the kind of 20x potential improvement, again, very, very compelling. But the questions are around manufacturability. How do you deal with mismatch in the analog circuitry? How do you make sure that the analog yields are high? It looks like a great idea in theory, but we've seen companies trying to bring this similar kind of technology to market and struggling to get it to work. So what are you guys doing differently to try to solve those problems? And what is it going to take to really get this kind of analog computation into the market? It looks like you're muted again.
Yeah, I think you're okay. The first task that we have is we have to convince ourselves, right? And so we have the advantage that we're not a startup. We don't have funding agents coming to us every quarter and saying, what have you got for us lately? We have this. We've given ourselves some time to work on this. We've brought in partners to help us ask these really hard questions. And so people who do want to see what we're doing in real time, I encourage you to explore joining the AI Hardware Center. But I think our first task is to convince ourselves that we can solve all these things. And all of us internally, when we work on this, we're all very aware of all these issues, right? We know why analog circuits have not, become general compute, right? Why everything is done with digital. Right? But the idea is that if you have something that in digital, you can literally get down to 4 bits or 2 bits and throw away all that precision that we usually need for digital workloads. If analog is ever going to work for anything, it's going to be something like this. So we definitely have focused on all sorts of the offsets issues, the noise issues. That's why we have to design clever things, and then we have to prove it to ourselves in silicon. And that's why it's important to have access in Albany to prototype 300 millimeter capabilities, where we can make, essentially design real circuits on 300 millimeter and actually put real phase change memory devices on it, long before we can justify the issue of working with partners to put it into a foundry that would be able to do it at high volume, right? So we prove it at low volume, and then we can make the argument that we need to go to high volume. We've solved all these problems and we prove that with real hardware.
Okay, sounds good. A question about, you talked about ISO accuracy when you're trying to use the lower precision. Can you explain what you mean there? Is that the same accuracy as the previous implementation, or what implementation, or the best implementation? What are you comparing to?
Well, in general, you usually mean the baseline from doing it the conventional way, either with floating point 32 or with floating point 16, whatever you're competing against. When you get down to the nitty gritty, you have to be really careful when we're talking about tenths of percent, because literally the way this deep learning works is you randomize the weights when you start. which means if you take the same hardware and you train the same model 10 times in a row, you're going to already have some fuzz from shot to shot because of that stochastic variability. Stochastic variability in how you initialize the weights, and stochastic variability in the stochastic that's in the stochastic gradient set, the order in which you show the examples. Did I put the apple before the banana or after the banana? You literally will get a different trained network every time. And they all go to pretty good accuracy, but there will still be some fuzz. So when you're literally getting down to, does it have the same accuracy by 0.05%? That's not a question that makes much sense, because you're going to, when you do this for production, you're going to get 5 shots, 10 shots at it. You're going to take the best model, or even something that votes the 3 best models, or so on. So we have to be careful about how finely we sand this down.
Right, right. So when IBM is developing these technologies, I mean, can you talk about how they're going to get into the market? Are you going to work with partners? Are there specific companies that you would co-develop with?
Well, I'm not an IBM manager, so I can never say IBM will do this or IBM will do that. I can state the facts. We used to own a fab. We do not own a fab anymore. We know that to make this real, to even be able to buy the products in the volume that we would need to put into our own cloud system, we'll have to work with a real foundry. We'll have to partner to make this happen. How we go about that, that's a question that you would need to ask IBM management. And to be honest, it doesn't make sense until we've really convinced ourselves, first with the digital, that our ideas, not just doing bfloat 16 like everybody else is doing, but really making product at FP8 training. We need to convince ourselves that that's really going to work. And again, we convince ourselves with hardware prototypes.
Okay, and a question about on the analog, are there endurance issues when you're using the phase change memory, and how does that affect the way these devices would be used for inference or training?
Yes, there definitely are. One of the issues with these merging non-volatile memories is there are always endurance issues. To a certain extent, you're already going to probably need to over-provision to deal with yield issues, so that over-provisioning helps you in terms of dealing with the lifetime of the part. But if you're nervous about this, I will remind you, you're probably all using laptops which have SSDs on it. And every device on that SSD, if you cycled it, you could fry it in less than a second, right? It only has a lifetime of 10 to the 4, 10 to the 5 cycles. And yet you have thrown out your hard drive and you have your entire life on that device because there is enough over provisioning and wear leveling and all those things to actually have it work for you for the 3 years you're going to own the laptop. So all of these devices that we're talking about are going to have endurances higher than what Flash has.
Right, good point. All right, well, that's all the time we have. So Jeff will be able to answer more questions during the breakout sessions.
Right.
So I see we have a lot of questions, a lot of interest in this topic. And so I encourage you to attend the breakout session and ask your questions there. So I'd like to thank Jeff for his presentation. And then we're going to move into a short 10-minute break. And after that, we'll be talking about the network edge. So thanks, everybody, and we'll see you soon.